What is artificial intelligence and why there is global interest? Now, what is intelligence? Artificial intelligence is changing how we interact online, how we manage our finances, and even how we work. All but the simplest human behavior is ascribed to intelligence, while even the most complicated insect behavior is usually not taken as an indication of intelligence. What is the difference? Consider the behavior of the digger wasp, Sphex ichneumoniaeus. When the female wasp returns to her burrow with food, she first deposits it on the threshold, checks for intruders inside her burrow, and only then, if the coast is clear, carries her food inside. The real nature of the wasp's instinctual behavior is revealed if the food is moved a few inches away from the entrance to her burrow while she is inside. On emerging, she will repeat the whole procedure as often as the food is displaced. Intelligence, conspicuously absent in the case of the wasp, must include the ability to adapt to new circumstances. One of the most important aspects of AI is that it is a multi-use technology. Like electricity, it can be applied in lots of different ways to lots of different scenarios. There is no single universally accepted definition for artificial intelligence, but the Oxford English Dictionary defines AI as the capacity of computers or other machines to exhibit intelligent behavior. This means AI systems appear to think, learn, and act like humans, and in some cases exceed the capabilities of humans. AI systems can analyze vast amounts of data, solve complex problems, make decisions, and perform creative tasks. Some AI technologies have been around for more than 50 years, but advances in computing power, the availability of enormous quantities of data, and new developments in software algorithms have led to major AI breakthroughs in recent years. It is these three components of advanced algorithms, data, and computing power that explain how machines can exhibit intelligent behavior and why AI has suddenly exploded into our everyday lives. Methods and goals in AI symbolic versus connectionist approaches. AI research follows two distinct and to some extent competing methods, the symbolic or top-down approach and the connectionist or bottom-up approach. The top-down approach seeks to replicate intelligence by analyzing cognition independent of the biological structure of the brain in terms of the processing of symbols, whence the symbolic label. The bottom-up approach, on the other hand, involves creating artificial neural networks in imitation of the brain's structure, whence the connectionist label. To illustrate the difference between these approaches, consider the task of building a system equipped with an optical scanner that recognizes the letters of the alphabet. A bottom-up approach typically involves training an artificial neural network by presenting letters to it one by one, gradually improving performance by tuning the network. Tuning adjusts the responsiveness of different neural pathways to different stimuli. In contrast, a top-down approach typically involves writing a computer program that compares each letter with geometric descriptions. Simply put, neural activities are the basis of the bottom-up approach, while symbolic descriptions are the basis of the top-down approach. Artificial General Intelligence, AGI, applied AI and cognitive simulation. Employing the methods outlined above, AI research attempts to reach one of three goals: artificial general intelligence, AGI, applied AI, or cognitive simulation. AGI, also called strong AI, aims to build machines that think. The ultimate ambition of AGI is to produce a machine whose overall intellectual ability is indistinguishable from that of a human being's. To date, progress has been uneven. Despite advances in large language models, it is debatable whether AGI can emerge from even more powerful models or if a completely different approach is needed. Indeed, some researchers working in AI's other two branches view AGI as not worth pursuing. Applied AI, also known as Advanced Information Processing, aims to produce commercially viable smart systems, for example, expert medical diagnosis systems and stock trading systems. Applied AI has enjoyed considerable success. In cognitive simulation, computers are used to test theories about how the human mind works. For example, theories about how people recognize faces or recall memories. Cognitive simulation is already a powerful tool in both neuroscience and cognitive psychology. Large language models and natural language processing. Natural language processing, NLP, involves analyzing how computers can process and parse language similarly to the way humans do. To do this, NLP models must use computational linguistics, statistics, machine learning, and deep learning models. Early NLP models were hand-coded and rule-based, but did not account for exceptions and nuances in language. Autonomous vehicles. Machine learning and AI are foundational elements of autonomous vehicle systems. Vehicles are trained on complex data, e.g., the movement of other vehicles, road signs, with machine learning, which helps to improve the algorithms they operate under. AI enables vehicles systems to make decisions without needing specific instructions for each potential situation. In order to make autonomous vehicles safe and effective, artificial simulations are created to test their capabilities. To create such simulations, black box testing is used, in contrast to white box validation. White box testing, in which the internal structure of the system being tested is known to the tester, can prove the absence of failure. Black box methods are much more complicated and involve taking a more adversarial approach. In such methods, the internal design of the system is unknown to the tester, who instead targets the external design and structure. These methods attempt to find weaknesses in the system to ensure that it meets high safety standards. Is artificial general intelligence AGI possible? Artificial General Intelligence, AGI, or strong AI, that is, artificial intelligence that aims to duplicate human intellectual abilities, remains controversial and out of reach. The difficulty of scaling up AI's modest achievements cannot be overstated. However, this lack of progress may simply be testimony to the difficulty of AGI, not to its impossibility. Let us turn to the very idea of AGI. Can a computer possibly think? The theoretical linguist Noam Chomsky suggests that debating this question is pointless, for it is an essentially arbitrary decision whether to extend common usage of the word think to include machines. There is, Chomsky claims, no factual question as to whether any such decision is right or wrong, just as there is no question as to whether our decision to say that airplanes fly is right, or our decision not to say that ships swim is wrong. However, this seems to oversimplify matters. The important question is, could it ever be appropriate to say that computers think, and if so, what conditions must a computer satisfy in order to be so described? Artificial intelligence examples. Though the humanoid robots often associated with AI, think Star Trek, The Next Generation's Data, or Terminator's T-800, don't exist yet, you've likely interacted with machine learning-powered services or devices many times before. At the simplest level, machine learning uses algorithms trained on datasets to create machine learning models that allow computer systems to perform tasks like making song recommendations, identifying the fastest way to travel to a destination, or translating text from one language to another. Some of the most common examples of AI in use today include ChatGPT uses large language models, LLMs, to generate text in response to questions or comments posed to it. Google Translate uses deep learning algorithms to translate text from one language to another. Netflix uses machine learning algorithms to create personalized recommendation engines for users based on their previous viewing history. Tesla uses computer vision to power self-driving features on their cars.